Okay, welcome. So what we're going to be covering today is an introductory lecture on forces. I'm going to go ahead and share my notes with you. Um, so there they are. And basically what I want to do is I want to introduce the concept of forces as well as just kind of give you a sense of some of the forces we'll be dealing with. And then start to get into Newton's laws, because Newton's laws are basically how we're going to connect this idea of forces to the ideas of motion that we've already discussed. Okay, so starting off with forces. And so the first question, what is a force? Now, there could be a number of different answers to this. I'm going to throw something that was said in the lecture. I'm going to throw that off to the side. I had someone say that a force is equal to mass times acceleration. Now, this is actually a statement of Newton's second law. This is not quite correct. First of all, it's this equation I would argue is incomplete. I made this case in class. Like there needs to be a descriptor about what this force is, because it's not true that every force causes an acceleration. Okay, there is a connection between force and acceleration, but it's more complicated than just F equals ma. And I think this equation makes much more sense if if there's a descriptor there, but we'll get to that in just a minute. Um, Basically, what I mean when I want to answer this question, what is a force? I basically just mean just something very perceptual. A force is a push or a pull. Now, when and forces were conceptualized long before we had a way to measure them, and long before we had a way to understand their impact on motion, or before we accurately understood their impact on motion, I should say. One way to measure forces, like the most commonly measurable force is weight, or the force of gravity. We'll get into that in a bit. So this happens to be why weight and force is connected, and why the imperial units of force, as we'll talk about, are in fact their units of weight. But fundamentally, a force is just a push or a pull. Now, the idea, another aspect of this is that a force is a vector. Magnitude, so the strength of the push, or the pull, you can think about the magnitude, but also the direction. A force upward is very different than a force downward. Okay. Force to the side is different than a force downward. All these things are relevant when it comes to forces. Now, the very important thing about forces, and one of the main analytical tools that we're going to use, and it's important to know, so I'll even put this in bold: individual forces combine vectorially. Okay. So basically, when you have multiple forces acting together in tandem, an example of this might be if you had a box and you had someone pulling it upward on one side and someone pulling it upward on the other side. So we could call this F1 and F2. Basically, what you would have, and I'll do this in a different color, is you would have a net force upward in that direction. And basically, F1 and F2 would combine vectorially. Now, that's not a graphical representation, but the argument is that that those two forces combine vectorially. And if you were to combine those vectorially, you would see that basically the left and right components of F1 and 2 would cancel each other, and there would be a combination of the forces in the upward direction. All right. That leads to this next point. This idea, F net, this is the vector combination of all forces on an object. Okay. And when it comes to, we're not going to get to Newton's second law in this lecture, but when it comes to Newton's second law, remember this F equals ma. Turns out that, again, it's actually F net that is equal to ma. Now, when people say F equals ma, there is an implied F net, because if there isn't, then that statement is not actually true. It's not true that any force equals ma. It's the combination of all forces on a particular object that is equal to ma. And I do wish, again, the F equals ma it's been popularized. It's something that everyone has heard of. And if you've ever, the Star Wars Day, may the fourth be with you, or the F equals ma day or whatever. And you so the point is that when you actually use this, remember that it's fnet. Okay, so I'm gonna state that now. I will state it again because it is important. People will get into trouble if they start just using F equals ma, and I have seen it before. You can't just pick a force and then set that equal to ma. You have to find the F net. All right. Now, last thing to talk about before we move on to types of forces is units of force. The SI unit is the Newton. This is just, the symbol is N. And it's worth noting that 1 Newton is equal to 1 kilogram per meter, or 1 kilogram meter per second squared. Okay. And basically the idea is that you're basically measuring there's some implication in this. Once you know the cause of what forces do to massive objects, it becomes much easier to quantify the measurement. But until then, it's somewhat difficult. And this is why the older unit, the imperial unit, is the pound. And a lot of people think the pound is a unit of mass. It is not. It is a unit of weight. Okay. Now, the distinction between mass and weight is not super relevant on the surface of the Earth. It is relevant in orbit, where things are effectively weightless. Nevertheless, more massive objects still take more effort to move, even if they are effectively weightless. It's not necessarily intuitive, but moving around a gigantic, massive 1-ton object does take more effort than moving around a 1 kilogram object. It's just that is how it goes, even if they don't have any weight. So that's kind of where the distinction comes up. Tends not to be as relevant to distinction. Nevertheless, because weight is a force and mass is mass is just a mass. Mass is a scalar, force is a vector. There are distinctions that you need to be aware of. And basically the SI is going to be the thing that we will use the unit we will use for the vast majority of our analysis of forces. Now, the next thing I want to talk about is different types of forces. And I kind of want to give you a survey of the different kinds of things you will see, some of which you won't see as much in this class. But we can generally divide forces into 2 categories: contact forces and non-contact forces. Now, the symbol is non-contact force, and the one that we're going to be worrying with by far the most is the force of gravity. So call that gravitational force. Actually, I don't want to do this in bold, so gravitational force. Now, an alternative name for gravitational force, and the name you're probably more familiar with, is just weight. Okay. If a physics problem is telling you an object's weight, they are telling you its gravitational force. Okay, so that is definitely worth remembering. All right. Now, the symbol I often use for gravitational force is just F with a subscript G, and it is equal to m times G. Okay, just mass times the gravitational acceleration. Now, this is an assumption. This is the near Earth approximation of this. If you wanted the non-near Earth approximation, which we might cover a little bit, it looks like this. It's G m1 m2 over r squared, where G is the gravitational constant. It is equal to the following: 6.67 times 10 to the negative 11th, and the units are Newton meter squared per kilogram. Basically, this is a constant that is needed in order to make sure our units work out. It's kind of the way that goes. Now the point of that is the gravitational force is actually proportional to the two masses that are being attracted. There is a gravitational force that always requires two massive objects divided by the square of the distance between the two. Now, the idea here, the connection between these two symbols is that lowercase g, and that's just the g we've been using for gravitational acceleration, 9.81 meters per second squared. It's just equal to capital G times the mass of the Earth divided by the radius of the Earth squared. And you can go look these up. If you look up these numbers, you use this for capital G. You can look up the mass of the Earth and the radius of the Earth in SI. So it's got to be in meters and in kilograms. Can't be in kilometers or grams or whatever. You will find that this calculation does yield, 9.81. That's what you get. Now, important thing to note, some people will say gravitational force is constant. It's not, all right? Gravitational force, even in near Earth, is not constant. What is constant is gravitational acceleration. That's not the same thing as gravitational force being constant, okay? The idea here is that the force needs to increase in order to accelerate more massive objects at the same rate. And we'll get into that when we talk about Newton's second law. But that's one thing. The other thing about it is just because another thing to note about this is just because an object has a force of gravity does not mean it's accelerating with g, okay? An object only accelerates with g if it's in free fall, namely if gravity is the only force on it. However, unless you're one of the lucky few who has been into orbit, and even in orbit, you actually have a gravitational force. What you don't have is a little different, but you will always have a gravitational force on you. Does not mean you're in free fall. You might have other forces on you. And that is where this next thing comes in. A force that is commonly encountered in the problems we will deal with kind of goes hand in hand with gravity, particularly if objects are in contact with the surface, is something we call the normal force. Now, basically what a normal force is, it is a contact force that prevents objects, actually we'll say solid objects from passing through one another. All right. Now, quick distinction between contact and non-contact forces. Contact forces, basically, it means exactly like it sounds. It means that the force originates due to the contact of two objects. You can't have the force without the two objects being in contact. So with the case of a normal force, you can't have a normal force without the two objects being in contact. Gravity does not require the two objects being in contact. Now, there are gravitational theories that basically postulate that, not postulate, but they predict, and it's how we observe this is still kind of unclear. This is why it's I don't know if it elevates the theory. It's more a gravitational hypothesis. But the idea is that there are actually massless particles, kind of like light, except not light, that exchange and cause the gravitational force. That's way beyond the scope of what I want to get into here. But the point is, we divide them into these categories because from our perspective, gravity does not appear to, these objects do not appear to be in contact with one another. Now, normal force is not just to keep, the way you can think about it is I'm sitting in this chair, and gravity's pulling me down. The reason I'm not accelerating due to gravity is because the chair is pushing back up on me. It's not letting me pass through it because we're both solid objects. That is what we mean by the normal force. Now, it's not just to do with gravity. Anytime, and it doesn't have to just be up, for the chair on me, it is up. But it turns out, if I lean back, the chair doesn't let me go backwards. So the chair is actually pushing kind of towards the screen as well. If I were to, push my desk and I slide myself away, we would often say colloquially, I pushed off the desk. That's not inaccurate to say, but the reason I moved is actually because the desk pushed back on me. Now that we'll get into that's a Newton's third law, but basically it was actually the normal force of the desk that pushed me away from the desk. Now, the normal force only did that because I pushed on the desk. That's a Newton's third law thing. So we'll get into that. But that's the idea behind the normal force. Now, this word normal, it doesn't mean common or usual. It means in mathematical lingo, normal is a term that will mean perpendicular to. So this is a contact force that is perpendicular to a surface. Okay. Now there is another contact force that is parallel to a surface, and that is friction. Another common force that we'll be dealing with. This is a contact force that is parallel to a surface. Now, in the case of friction, we can have really two different types that we'll talk about. The symbol you'll often see used for friction is lowercase f. So this stands for the force of friction. F sub s is static friction. And F sub k is kinetic friction. Now we will get into these kinetic friction. We will get into these more. Maybe this week, maybe next week. But the idea behind static versus kinetic friction is you can imagine you have a book, you push it across the table, and basically as it moves across the surface, friction slows it to a stop. Now that is kinetic friction. So kinetic meaning motion. So it's the friction that occurs between two surfaces that are moving against one another. But you could also have the case where you have the book on the table and you slightly elevate the table. Now, if you were to do that with effectively a frictionless surface, the book would slide off the table. But in most tables, and the rougher the table, the better, the book will stay there as long as you don't make it too steep. That is static friction. So that is the friction that occurs between two surfaces that are not moving. So that's the upshot with friction. Okay. Now, another common force that we will see in this force unit is it's a broad category, and I just call it applied force. Symbol I tend to use for this is capital F with a subscript of A. Not always. I might do, like, if it's from a person, it might be F sub P. If it's from an engine, it might be F sub E, whatever. But applied force is it's a general sort of category. And basically what this means is it's a force applied by an external agent. So in this case, and generally the key here is we're not going to analyze the causes of that force or calculate anything about that force. Typically, that force will just be given, or potentially we'll need to solve for it. But the idea here is it's like any force from a person. Okay, so like an example of this, common example in this unit of physics, is a box being pushed across a floor. Now, in that case, you have to worry about a bunch of forces. There's gravity on the box, there's the normal on the box, there's the friction on the box. But in order for anything interesting to happen, you also need some sort of applied force, whether that's from a person or from, a little motor or something, an animal maybe, that is what we're talking about when we're talking about applied forces. Okay. Another type of force we'll be dealing with, occasionally a little bit, will be drag force. This is also a force that it's somewhat similar to friction, but it has more to do with an object moving through a fluid material rather than two surfaces moving against one another. So drag force has to do with the contact of like air or possibly water or some other gas or liquid, an object moving through that. Now we'll touch on that, but we'll not go into that in any great detail. So drag force. We'll also have a spring or elastic force. This is one of the ones that we can actually find a law for, which is um Hooke's law is what we'll be using, and it could be considered a type of applied force, but because we'll be analyzing it uniquely, we'll put it into its own category. Another one we'll look at is the tension force. Tension forces, these are forces in ropes or cables. Again, could be a special type of applied force, but again, tension forces will have special rules that other applied forces won't have. That's why I put them in their own category. One we'll touch on much later will be the buoyant force. If you don't know what the buoyant force, basically this is the floating force. An object that, or a force that causes objects to float is the buoyant force. Turns out buoyant forces are on objects that even that aren't floating. Any object immersed in a fluid has a buoyant force. And we will, like I said, we will talk about that. Okay, now we've only had one non-contact force so far that I've talked about. The other two, really, it's just one, but we'll talk about them distinctly. We'll talk about two aspects of it, is the electric and the magnetic force. Now, this combines into the electromagnetic force. Turns out those are part and parcel of the same thing. They are connected in ways that no other forces are. So, electromagnetic force. That constitutes really the second non-contact force. The third and fourth non-contact forces are the weak nuclear force and the strong nuclear force. Now, I will really not bring this up much after today. We're really not going to worry about these very much, at least definitely not about the details of it, where it comes from, modeling it, anything like that. Suffice to say, basically what you can think of, these forces are the forces that hold nuclei together, and there are two of them that have been defined. Why is this needed? Well, what a nucleus is, it's basically a clump of particles, some of which are neutrally charged and some of which are positively charged. And the idea is that those positively charged particles, remember, like charges repel, they should repel one another if all they're worried about is electric charge. However, they don't. They stay stuck together in those nuclei. And the reason for that we understand is the nuclear forces. Okay, so these are the things that hold nuclei together. That's basically what that is. And like I say, that is really the last that I'm going to talk about it. So really those won't be touched, just for completeness sake, I'm including. But everything else here we'll deal with at least a little bit on this list. Okay. So last thing I want to talk about in this lecture is forces in motion. So how do forces affect motion? Well, the old view, going back to ancient Greece, is that forces cause motion. And really what is meant by, there's a sense in which that's accurate, but it's not very precise. Really what they meant by this is that forces cause velocity. So if an object has a velocity, then there must be a force acting. Now, it turns out there are some problems with this view, but hand in hand with this is the idea that the quote unquote natural state of an object was at rest. Now, this is not how we look at physics anymore. We have a different conception of the natural state, and I'll get into that in a minute. One problem with this is the idea is how does projectile motion work? Okay, so like, if you can imagine, you throw a ball it's very clear what the force on it is as you're throwing it, right? It's your hand, and your hand is pushing on the ball. The point is that once it leaves your hand, well, is your hand exerting a force on it anymore? Well, not really. Like we don't have a way to, we don't have a way to exert forces with our hands without touching something. Like we're not wizards. We can't, or we're not Jedi. We can't point our hand at something and then exert a force on it with our hand. We actually need to touch it if we want to exert a force on it with our hand. Nevertheless, a ball you throw, it seems to have some impact from your hand on it. And so this was one thing that wasn't quite understood. There were a couple of different ways that the old view attempted to do this. One was that the moving object created basically a vacuum behind it, and air came in and continued to exert a force on the object. That turns out to be incorrect, not even close. Another one was this concept of impedance, impetus, impetus, impetus or impetus. And that basically what your hand did is imparted a certain amount of impetus to an object that was then lost. Now that model is a little bit more difficult to show why that's incorrect. I'm not going to go into that. That's more of a history of science thing. It's interesting, but I'm not really going to go into that. But what I will say is a big part of this. It wasn't so much how do things move as the kind of big question was the questioning this natural state of an object. And Galileo questioned this. So Galileo, most famous for his revival of the Copernican model, and really not just his revival of it, but the fact that he advocated for it in his life. But he actually discovered quite a bit about motion as well. And the two ideas it turns out they were connected. But basically, Galileo rejects this idea. And what he does, the reason, well, here's it, and his point was, he's like, okay, if we take this seriously, then the idea is that naturally things will just come to a rest. And that's fine. We see that, you pick up a rock, you throw it. It comes to a rest. You kick a ball, it comes to a rest. You drop a pail of water down a mountain, eventually all that water comes to a rest. You see an avalanche, eventually all that snow comes to a rest. But he also acknowledged that maybe that it's the object's natural tendency to want to do that, but maybe not, because there are certain things that can make it come to a rest faster. So if we just think about a book, you push a book on a perfectly smooth table, it will slide and eventually come to a rest. But you put it on a rough table with, approximately the same force, it'll come to a rest much faster. Why? Well, there's more friction. So he's saying, well, maybe there is this property where objects want to come to a rest, but we also know that friction can increase that. So if we really want to get at this at an object's natural propensity to come to a rest, we have to eliminate friction. And Galileo did this with this kind of clever experiment with very low friction tracks and a ball. And basically what it looks like is there's kind of like two ramps, and it kind of looks like this. So it's I'll do it a little bit better. I can do better. So it kind of looks like this. And the idea here is he would let a ball, and the ball would roll down the ramp. And this is very low friction. Not zero friction, but he got it to very low friction, as low as he could get. And you can do this by making the track very smooth and making the contact points low. And basically what he saw when he would do this is the ball would go down and it would start coming back up, as you would expect. Now, how far up did it go? Well, basically it went up. If you drew a horizontal from where it started, it basically went up that far. Now, I will post a video of this in a video of a modern example of this. But basically what happens is it goes up as far as it started. And it didn't matter what angle he made this at. He could make the angle really, really slight. It would go further up that ramp the longer you make that portion, the the more difficulty you have with it because friction does start to come in. But the point is that the closer you get to eliminating friction, the closer you get to these things coming up to equal heights. So his, in the limit, he says, well, I can't completely eliminate friction, but if I could, these things would come up to the same heights. That's what it's approaching. That is the net effect that limiting friction has. Now, he does a thought experiment. Now he can't do this because you can't actually set this thing up. It would require an infinite amount of space. But he's saying, okay, what if instead of having the other side go up, I have, I still have this first side angling down like so, but then not a very good, but then I just have it go straight. Okay, never comes back up. Right side never comes back up. Well, the point here now is that if you let this thing go, and if there, again, assuming there was no friction, you can never actually eliminate friction, but you can kind of get a picture of what would happen if friction was eliminated by continually reducing it. So how far will this thing go? Well, his point is that, well, if on the one above, it's going to go all the way up until it gets to its original height, and this track below, because it never comes back up, it never gets back to its original height. His thought experiment indicates that this ball will go forever if there's no friction. Okay. Now, again, you can never actually eliminate friction, but the point is that what his investigation is indicating is that the closer you get to eliminating friction, the more likely this thing would be to just go on forever. Okay. And that is revolutionary because it rejects this idea that there is a natural state at which objects come to rest. So it rejects that objects naturally come to rest. He will say that, this happens, but it basically happens due to friction. The reason why objects come to rest on the Earth is due to friction. And there's a certain aspect in which you watch the moon, the sun, the stars, sort of go around from the perspective of the Earth. You watch that, those things never seem to come to rest. They just go on and on and on. And as far as Galileo knew, they had gone on, as long as mankind had been around. So they kind of dovetailed with that, in that we have this constant motion. And there was this kind of hand wavy explanation, the old model, that these were special objects that had their own kind of natural motion. But Galileo saying, no, basically all we need to say is that there's no friction up there. And that means that these things will just kind of naturally just continue on. Now, it turns out that there is a little bit of resistive force up there, and this causes a number of different things to happen. But that's very difficult to observe in a much later discovery in science. But the point of all of this is that Galileo rejects this idea of objects naturally coming to rest, and he comes up with the idea of inertia. Okay? And what inertia is, basically, inertia is this idea of inertia is that objects tend to do whatever they were doing before. So if you want to know what an object's going to do in the future, you look at what it's doing now. Now, the caveat to this is unless acted on by a force. Okay, so forces can change this. Forces can impact inertia, but they can kind of change on by a force. They can kind of change what the inertia is. Face a force. They can change what the inertia is doing, but without forces, objects will change. Will just continue doing whatever they're doing. So, if an object in motion will stay in motion, you may have heard it this way: an object in motion will stay in motion. And an object at rest will stay at rest. All right. So that is what Galileo is saying here. Okay. He's saying that that this is what's going on. And thus what forces are doing, forces cause a change in velocity. So basically, forces cause an acceleration. Now, Galileo, because he didn't fully appreciate the vector nature of forces, velocities, and accelerations, he didn't quite have the full picture of this. It was Newton that came along and really made the picture. That's why we call them Newton's laws. Galileo thought he didn't distinguish between speed and velocity. So he thought that that the objects going around at a constant speed, like in orbit, he thought there didn't need to be a force to cause that. Okay, turns out there does. And the reason is those objects may be going at a roughly constant speed. Their speed does change a little bit, but they're definitely not always going in the same direction. And you need a force to cause that change in direction. Okay. So and Newton was the one who realized that, which is why these are Newton's laws and not Galileo's laws. Galileo really didn't have a grasp of the third one, as I understand as well. But he kind of understood the first two, just not really in their vector form. So we'll get into that. We're not going to cover all of those today, but really, this kind of led into Newton's first law. And sometimes this is just called the law of inertia. And basically, what Newton's first law says is that if F net equals 0. Now, note, this is not saying that F equals 0. It's not saying F equals 0. It's saying F net equals 0. Okay? So this is not saying that if there are no forces on the object. I mean, there could be no forces on the object. That's very difficult to imagine. I don't know that that could ever actually happen. But it's saying that the combination of forces on the object is equal to 0. If F net is equal to 0, then acceleration equals 0. Okay. Now, F net equals 0. If this is true, we say that the object is in equilibrium. Okay, so if you hear that term, object in equilibrium, it means different things in different contexts, but in the context of forces, it means F net is equal to 0. And the idea here, another way to put this, is that an object in equilibrium is at constant velocity. Okay? This does not mean that that constant velocity needs to be at rest, okay? An object in equilibrium could just be going along at a constant velocity without changing either its speed or its direction, okay? So this is the big difference, is that, the old view was that objects at equilibrium had to be at rest. That's not what Newton's first law is saying. Newton's first law is saying that objects in equilibrium will not accelerate. Okay? If the forces are balanced, if the net force on an object is 0, then its acceleration is zero. Now, the Newton's second law gets into, well, what happens if the net force is not equal to zero? Well, obviously, then there will be some acceleration, but there is a question of how much acceleration. And turns out that depends on the object. And that is where Newton's second law comes in. Now, I'm going to end things there. We'll get into Newton's second law, probably the third law in the next lecture, but I'm going to stop things there. So thank you for joining me and have a wonderful day.